conference will now be recorded.
Welcome, everybody. We'll get started here in a minute or so. Okay, it's my, for everybody who does not know me already, I'm Dr. Mary Beth Mealy. I'm the scientific coordinator for Geo Aqua Watch. Today, we are delighted to welcome you to another one of our webinar series. And we try to provide information that's interesting and relevant to the community. And we were delighted to hear from Brockmann Consult that they have made some recent improvements to the XCube workflow. So we invited them to come tell us a bit about that. And they wholeheartedly agreed. And so we're happy to bring to you on this World Mountains Day a presentation by two colleagues, a Brockmann Consult, Pontus Lurcock. He's a software engineer at Brockmann Consult with a strong focus on geodata cubes and analysis-ready Earth observation data. He has extensive experience working at the interface between informatics and geosciences and holds a Master of Science in Computer Science and a PhD in geology. And he will be giving the first portion of the presentation. If you're in the audience, if you could just mute your audio. We're getting a little bit of feedback. And then our second presenter, who will give us a demonstration of the workflow, is Clara Backens at Brockmann Consult. She's a software developer with a background in GIS and remote sensing. She holds a Master of Science in Environmental Geography and Management. Clara focuses on developing interactive visualization and exploration of multidimensional Earth observation data. And with that, I'm going to turn it over to you, Pontus.
Thank you very much, Mary. Thank you for the invitation, and thank you for everyone who turned up to listen. I think someone is still unmuted because I'm still getting a bit of feedback here. Okay, I hope everyone can see that all right. So yes, as Mary mentioned, we're going to be talking mainly about XCube today, our now, I guess, 10 years old or so Earth analysis, Earth observation data framework, environment, whatever we're calling it now, and some of the recent developments in this. And we'll be going through an Earth observation workflow to give a bit of shape and theme to the presentation. So quick overview at the start of what I'm going to be talking about. First, I'll introduce the company and the XCube ecosystem. Then I'll give a quick high-level overview, just to give an idea of what all the things that are in there, but it's only a 15-minute presentation, so we won't go into too much detail. And then I'll take a vague promenade through an XCube workflow from data ingestion, a little bit of processing, and then viewing, analysis, dissemination, just to see how you'd apply this to an actual scientific use case. And after that, I'll segue into the live demos from my colleague Clara, who's first going to present some Jupyter Lab notebooks and then the interactive web viewer. So first, a couple of words about Brockmann Consult. We're a small, I guess, more medium now, consultancy in Hamburg in northern Germany. I'm in the left-hand side of this organogram, developing software. XCube is by no means the only software in our portfolio, but it's quite a major component now, and it's a major contribution to the Python scientific ecosystem. Apart from that, the other branches are geoinformation services and expert consultation services that we provide to public bodies, private customers, have collaborations with universities, academics, companies. A lot of our work is for the European Space Agency. But today we're going to be looking at the software part of it. So starting at the beginning, on a very vague and high level, what motivated XCube? Tackling environmental questions with conveniently accessible data, so accessible and analysis ready, and other important buzzwords of this kind are going to be strong themes here. It's about collating this increasingly large and somewhat bewildering world of Earth observation and scientific data sources and marshalling it into a form where you can actually start doing useful scientific work on a defined use case without spending large amounts of time fettling your data into the right form and making sure that different data sources line up with each other. So this motivates the DataCube concept. It's about integrating diverse sources into a unified time and geographical cube structure. And apart from the data access and organization, we're also, I think somebody else needs to mute themselves. I'm getting a bit of, thank you, that's better. And the other end of the process then, apart from the actual data analysis, which XCube provides tools for, is the visualization, sharing, and dissemination, which we'll also look at towards the end. So, coming into the more specific requirements for what XCube is doing, convenient access to as many big gridded spatiotemporal data sources as we can find. So essentially, we have a standardized sort of data store structure for XCube, and it's rather easy to interface new sources to that. So we're continually adding more of these data stores to feed more data sources into XCube. Once it's in there, we present it as analysis-ready data, which effectively means standardized data cube with known properties. So the same workflows can be applied more or less unchanged to different data sources. And then adding functions and methods to the Python scientific ecosystem that help with analysis of these data cubes. And then at the other end, providing a web server for interfacing it to other cloud systems, a web visualizer, which you'll see later for more interactive analysis and presentation of the data and sharing it. And the whole thing is built upon Python's existing scientific stack. So we're not reinventing any wheels here. We're building heavily upon the Xarray, ZAR, and Dask packages, and essentially extending that specifically for DataCube applications and a few related areas. So moving on here, we have the sort of big iconic ecosystem diagram that every large project somehow grows. And you'll be relieved to know we're not going through all of this today, but this is just a sort of overview to show how diverse the applications and the components are of the XCube ecosystem. We have a few bits that we won't talk about here, like batch processing, GeoDB, the vector data. What we'll mainly go through today, in order to keep this presentation a little bit structured, is a sort of high-level scientific workflow direction, where we start from the data stores here at the bottom, these cylindrical objects. We go into the main XCube core here, and then we look at what we can spit out at the end after processing and analysis in terms of viewer, in terms of applications, and interfacing it to other systems. So it really provides an end-to-end solution, is the idea, and utilizes common standards for data representation, so that things, as far as possible, can be processed homogeneously without having to hand code special cases. And the whole thing is, well, the ecosystem it builds on is open source. XCube itself is open source. We implement specific projects for specific clients, and things are deployed in the cloud where there are paid services for the actual hosting, but the code itself is open source licensed and openly developed, and comments and suggestions and contributions are always welcome. So coming back to the data stores, which are going to be a major component of today's demonstration and presentation. Looking down here at the bottom left, we have a sort of structure diagram of a few of the main ones. The main division here is between the file system type stores here, the little cylinders at the bottom. So these are the ones that let you read data from your local disk, from object storage buckets in the cloud, and also to write it to anywhere we have permission to do that. So this is everything from FTP servers that have been running since the 1980s to the new modern AWS S3 buckets. So that's for data storage largely, but then we also have interfaces to all kinds of web portals and internet data provision services, things like the Copernicus Climate Data Store, stack catalogs of various kinds within the Copernicus data space ecosystem and in other places. Copernicus Marine Environment Monitoring Services, Land Monitoring Services, Zenodo. Essentially, if there's a useful looking online source of data somewhere, we can write a data store for it, and in many cases we have. Here to the right, you'll see this or something similar live in the demo later, but this is just a snippet from a Jupyter notebook looking at how this would look in a typical scientific workflow, and it's really just two steps here. First, open the data store. Second, select the data you want with time span, geographic area, and any other relevant things. And you already have your data cube there with the essential properties shown, and then you can start working with it right away. Brief excursion into one of the more recent developments. We've recently added a multi-source data store, which effectively adds a sort of extra layer of convenience on top of this. If you're doing a workflow using many of these diverse data stores, then you're no longer in this sort of one-step process here. You have to open various data stores and then open various data sets from those stores. If you have a well-defined workflow already, that might get inconvenient. And so we've implemented a store which basically pre-configures a whole bunch of stores that you're interested in for a specific use case, and then hides it under one sort of overarching multi-store. So we see the input stores at the bottom, and then this gets spat out into a standardized cube sampled to a consistent grid. Looking at that in Jupyter Notebook again, it's, if anything, even more simpler. We don't show the configuration. That looks a little hairier, but it only has to be written once for a specific workflow, and then you have this virtual data store where you can just open it with one configuration file, and then you have instant access, or rather, first it has to actually fetch the data and cache it, but after that you have it all available to you without any further ado. We won't go very deep into the toolkit for data cube processing here, because this is really a sort of grab bag of useful utilities, and what you're actually going to use depends on your use case and your scientific requirements. So once you've read in the data, XCube gives you the tools to process it, but it's up to you what you actually do. So just as one of the more useful examples here, XCube's very capable resampling framework. It's obviously a very common task in this kind of data analysis. You have heterogeneous sources. They're probably to some extent from all different grids, and XCube then lets you do everything from a simple affine transform for scaling or rotation to reprojection or full-on rectification from an irregularly spaced set of points onto a standardized regular grid. So looking at where this is actually used, We have quite a few online deployments, as I mentioned. Although the software is open source, you can use it locally, you can use it anywhere, but sometimes it's useful to have an online portal that just sets everything up for you. So we have a few of these portals: the Agricultural Virtual Laboratory EuroDataCube DPSDL, which we're actually going to use later to run the demo. And these just bring together processing facilities, a Jupyter Lab environment, pre-configured data stores, and so on. And then one of our longer running ones is CyanoAlert, which is a slightly different application, which is a live monitoring services for cyanobacteria, blue-green algae blooms, which can pull current data from satellite images and then push that as warnings to local bodies or individuals who've signed up for alerts on that. Looking now at the dissemination and publication end of the pipeline, we have the XCube server and viewer. So the server is one of the less photogenic parts of XCube, as you can see from the screenshot here, but it's actually very useful. It implements a lot of standard web interfaces, OGC, WMS, WMTS, an awful lot of 3 and 4 letter acronyms for various tiling and coverage services. So if you need to interface your data afterward, after processing, to some other standardized web service, and this is a very useful data clearinghouse, effectively, to transform between different formats and different interfaces. Much prettier is the XCube viewer, which actually sits as a front end on top of the XCube server. So the XCube server does the main processing work here, but the viewer is a very capable, user-friendly, interactive web-based analysis environment, which lets you analyze and visualize data, and you'll be seeing more of that later. Recent addition to the viewer is server-side plugins, which means that with quite a small amount of Python code written on the server side, this actually gets automatically interfaced to a corresponding widget on the viewer side. So this makes it far more extensible for specific use cases, and it's gradually evolving from initially quite a generic tool to something that can be very heavily customized for specific deployments. Looking further into the dissemination end of things, XCube is now involved in Earth code, which sort of aligns with many of the fundamental goals that I mentioned for XCube. So this is all about when you've finished a scientific project, that the code and the data doesn't just end up archived and forgotten on some local disk, but gets published in the cloud, cataloged, and it's, as we all like saying these days, fair, findable, accessible, interoperable, reproducible. So the code and the data can go out into the cloud and be cataloged and be available for reuse and building on. XCube provides a couple of tools within this workflow. One of them is XCEngine, which takes Jupyter notebooks and turns them into Earth observation application packages, which lets you plug them into cloud-based analysis workflows. And the data sort of counterpart to that is Deep Code, which essentially tidies up and verifies and catalogs output data sets and puts them into web catalogs. So this was a very brief and hopefully not too confusing tour through some of what XCube can do for you. If there is anything you'd like to follow up after this presentation, of course, we'll have time for questions after the demo, but it is all online, freely available. Documentation, installation instructions are online. There's a GitHub repository of code where you can also open bug reports, request new features, open discussions, and you can always email us if you have any questions or suggestions. And with that, I will let Clara take over and we can go into the live demos.
Yeah, thanks, Pont. I'm actually not the presenter, so I can't, now I can share my screen. Perfect. Okay, so it's my turn now to show you how to use XCube to access some data sets and also visualize them at the end. So we will start with some basics regarding the XCube store, and then we will build some Sentinel-2 cubes. We will access some ocean color data from Zenodo and from Siemens. So let's get started. So the XCube store, you have to install that Python package in your environment, either with pip or with Conda Forge. So this is like the base, and then you can create, as Pon said before, some XCube stores either for your local file system or an S3 bucket, and this is what we will do in this notebook. So I will go through a couple of notebooks which are also in a GitHub repo, so maybe Pon, you can share that in the chat. And if you want to access other data sources, like Pon said, the Sentinel Hub or Zenodo or the Copernicus Marine Service, you have to install another plugin, and then you can create XCube stores for that. But let's get started with the basics. So if you're getting started and you want to find out if your plugin is actually installed in your environment, and you can use the list data store IDs, and then you see all the plugins that are installed in your Python environment, see all the file store systems at the bottom, at the top. We also see that the Zenodo is installed and Siemens, so everything that we need for this demo. So next, when you want to get started in creating your store, you have to know which parameters might be necessary for creating a store. So you can use the get data store param schema for your store of interest to get all the infos that you need to create that store in the next step. So the most important part or method is the new data store method. Here you are saying that you want to create a XCube store for a S3 bucket. Then you give it a root, which is in this case a path to a S3 bucket, which is here stored in a environmental variable, so you can't see that. And we also need to give some key and secrets or credentials because it's a private bucket. But with that, you are creating a store. So now you have a connection to that S3 bucket. And in the next step, you can list all the data IDs that are available there. So you can see a bunch of ZAR files and a level file. If that list would be super long, you can, and you have a data set in mind, you can check with the has data method if it's available. And then when you decided which data set you want to open, you use the open data method. And again, as each data source and each data set is a bit different, you want to know the opening parameters for that. So again, there is an open data param schema that lists all the opening parameters that you might need for your data set of interest. And if you have a specific data set in mind, you can also pass along the data ID. But now to the most important part is opening the data with the open data function. And so you just, in this case, give it the data ID from your store, and then you can open the data. It returns an XArray data set, but this operation is lazy. So it only returns the structure of the data set. So you can see the dimensions. So it has 7 time steps. You see the data variables. You can take a look at the attributes of the specific variables and the chunking. And then if you want to write the data or plot it, then it gets actually loaded. So in the next step, we are plotting the second time step of this data cube, and now the data actually gets fetched. So these are the basics. And now we want to build up on that knowledge, and we want to start with accessing a Sentinel-2 data source. And you can do this, for example, with a Sentinel Hub XCube store, but you can also utilize the XCube Stack plugin, which allows you to access a variety of different stack catalogs. And now the XCube plugin that you've installed before is enough. So you need another plugin that in this case is called XCube Stack, and you can install it in your environment with ConverForge. And before we accessing the data, some general information about stack catalogs. So stack stands for Spatial Temporal Asset Catalog, and it consists of catalogs and collections and items. And in our case now, each item presents a single observation which holds a timestamp and spatial resolution, not a spatial resolution, a spatial bounding box, and various assets, which can be, for example, the image bands. So each item has or corresponds to a specific time and place, which makes these stack catalogs actually queryable by the spatial and temporal extent of your study area of interest. But now to the XCube Stack plugin, we have a variety of different XCube Stack stores that you can actually initiate. And the easiest one is just a general stack store. With that, you can access every stack catalog that points to any ZAR or netcdf or geotiff. But as I said before, each source is a bit different. So when you now want to access some Sentinel-2 data for the planetary computer, for example, you can create a XCube store for the planetary computer stack API. And this returns single items. So if you want to have a proper XCube, not XCube data cube. If you want to have a proper X-array data set, so analysis ready data cube, we offer also the option to create a store for the planetary computer that supports at the moment Sentinel-2 level 2A data and with this specific ID. And this is what we are going to do now. So we are initializing a data store. So again, we're using the new data store function. And now some general information about Sentinel-2 samples that we want to have in analysis-ready data cubes. So the Sentinel-2 products are organized in stack items. So each item represents a single tile. And as you know, the tiles, they're overlapping, they are stored in the native UTM coordinate system. But if you want to have them in analysis ready data cube, something happens behind the open data function. This is what happens. So the stack API gets queried for all the items that are in your bounding box and time range. And then it gets sorted by time and ID. After that, it gets aligned and the overlaps are resolved. And if all the tiles are in the same UTM system, no reprojection needs to be done. If it is the case that you have tiles from different UTM coordinate systems, some reprojection gets done. And at the end, it gets assembled to one unified cube. And this is what we want to do now. So we want to access a small data cube for the smaller region around Stavanger in Norway. So this is our study area for this small demo. And again, we're using an open data function. We're saying that we want to have some Sentinel-2 level 2A data, give it a time range, give it a bounding box. Oops, we also say that we want to have a spatial resolution, but we are converting it to degree because we are also saying that we want the EPSG 4326 coordinate system. And then it's also possible to say which variables we're interested in. So in this case, we just want the bands 2, 3, 4, and 8. And when we are executing this will take a few seconds. The data, again, will be accessed lazy. So we just get the general structure of this data cube. So we see 3 time steps, some variables, the variables 2 to 8. And then when we want to plot the first time step, this is where the data actually gets loaded. So we see it here. This is just a small extent of the whole study area that we will look at the end. Yeah, so to our next data store, which is the CMEMS. No, not the CMEMS, it's the XCube Zenodo. So it's similar to all the other data stores that I've shown you before, but now we want to access a data set from Zenodo. For that, you need another plugin, which is called XCube Zenodo. You have to install that into your Python environment. And then I will open a new tab. I hope you will see that, which is the Zenodo page with the information or with the entry for the monthly gap-filled Ocean Color Climate Change Initiative dataset. So each dataset on Zenodo has a specific ID, which you can find here on the right. I hope you can see my mouse, and also in the URL. And this ID, we will take that to create now a new XCube data store for Zenodo. We give it the root, which is actually the record ID of that specific data set. So we have now a connection to that specific data ID. We can now list all the different data sets that are available and see that we have in total 2 zip archives with 2 different spatial resolutions, one in 1 degree, one 0.25 degrees. And when the file are compressed, you have to preload them first. And therefore we have a preload method, which I will execute now. And this method downloads the zip archives into your local folder. And it will decompress the archive and move them to your local file system, as you can see here on the left. Now we can access actually that decompressed file, and we see there is a netcdf, and then again can use the open data method to open the actual data set, which we can see here. Now we will do some adjustments and perform some spatial temporal subsets so that this data set is adjusted to all the other data sets that we will access so that it fits well and structured in the viewer. So we're doing some chunking, some spatial and temporal subsetting, and then converting some data from log scale to absolute scale. And now we can plot one-time step, as you can see here. And finally, if you want to save a cube like that, you can create an XCube file store, which allows you to write the data locally into your file system. So it created a new folder, which is called storage. And you can see that here on the left. And then here a few seconds ago, that file got modified. So I've overwritten it. Now to the last notebook that accesses data from the Copernicus Marine Service. So here again, this is an external data source. So you have to install another plugin, which is called XCube CMEMS with CondaForge. But then, as with all the other notebooks, you again are initiating a new data store for CMEMS. As we want to access multiple products in this notebook, we are defining a time range beforehand and a bounding box. And then we can take a look at the data set that we want to open. So this focuses on the Northwest Shelf region. It holds some chlorophyll and turbidity data. It's a level 3 product. And this is just the normal Siemens catalog page. When you go to data access, you see all the data sets listed under that product and with their specific IDs, which you can copy and then enter in your open data method, as you can see here. So again, we're using the open data method. We are defining the time range that we're interested in and the bounding box. Then we're doing some cleanup and some chunking. And at the end, we can plot the data. And we can again also, here we can see one time step. We can write it again to our local storage. In this notebook, we are also accessing 2 other data sets, one level 4 product with a 4 kilometer resolution, another with a 300 meter resolution. I want to be conscious of our time, so I will move on to the next step, which is actually visualizing the data that we've accessed in the XCube viewer. So the XCube viewer is just an extension of XCube. It's already installed if you have installed XCube into your environment, and you can use it to deploy it on a web page, but you can also run it out of your notebook. So the easiest way is the option 1 here. So you are creating a viewer, or you're initiating a viewer, and then when you've already opened some data sets, you can just add them to your viewer like this. And with viewer.info and viewer.show, you can visualize them and open them from your notebook. If you want to have some special settings, for example, you have some color maps that should be added to some variables, or you want to change some titles, you can also create a viewer as server config, which I have mine here just to the left in my folder. And then you can create a viewer like that. And you can use viewer.info with some links to the viewer, or you can directly show it in your notebook, as you can see here. But I want to open it in a new tab, so I will use that URL and go directly to the data set of interest. So we are moving to the first time step, and we can actually see nothing, but now we can see it. So this is the data set that we access from Zenodo. And on the bottom, on the top, we can select between all the different data sets that we have configured for this viewer. We can also select the different variables from the data sets. And what I do, I usually start by clicking through the different time steps, which you can do here at the top. It is also possible to create some geometries for your map. You can create some points which automatically are generating some time series, as you can see on the right. Or you can create some polygons or import your own geometries if you have them in a GeoJSON or a CSV. Now let's move to a finer resolution. We are looking now at a level 4 product, which we're now seeing chlorophyll A concentrations in a 4 kilometer resolution. The data is based on AllSheet data. This is one of the data sets that I skipped at the notebook before due to time reasons. And here again, we can create some time series again that are added to the plot on the right-hand side. And we can also turn on an info box with which you can hover over the data sets to see specific pixel values. And now let's move to the 300 meters, which is a level 3 product. So we can still move through that. Or when we now want to have an even finer resolution, we can open the 100 meter data set. Let's go to the 2nd of June, which you can see here. And this is based on Sentinel-2 data. And we've already also opened or created a Sentinel-2 data cube in preparation, a bit bigger one than the one we just generated in the notebook that I've shown you. And if we want to compare the different products, we can pin this data set right now to the left and open another one, the Sentinel-2 cube. And let's move to the 15th, for example. So now you can see on the, wait a moment, on the left side, you can see the chlorophyll product. And on the right side, you can see band 2 from the Sentinel product. You can also activate the RGB mode for that, as we have downloaded the bands, the red, green, and blue band, and then you can visually compare the data. Yeah, and it's already 1:41, so I would close here. And yeah, and back to you, Mary.
Okay, thank you so much. If anybody has any questions, you can use the raise hand function. Let me turn my camera back on. Or you can pop your question in the chat. We can ask that. I will start off with a question that I have, because I know several folks in the audience are they work with different satellites, such as OceanSat or maybe PACE. Is there an opportunity to upload some notebooks for other satellite assets in your XCube environment? I recognize that you were probably contracted to do the work supporting the European satellites, but is there information sharing or GitHub and Jupyter Notebook sharing capabilities for other researchers who want to use other assets?
I can probably answer this to some extent. Fundamentally, the data formats are usually one of a few well standardized and well known ones. So from our point of view, if a researcher needs to use a particular satellite data set that we don't support yet, then the question is where is this available? Is there a web portal or a cloud portal for it? Can we interface with this? And if it's not already in the catalog of one of the portals that we support, then it's usually a fairly quick job to write a new XCube data store for that. So in principle, we can support practically anything. In practice, it's an on-request situation where if somebody needs it and we don't have it yet or we don't support it yet, then we can add it.
So specifically those ones that I mentioned, maybe PACE or OceanSat. Do you have?
I have to say off the cuff, I don't know.
Okay.
I don't know where we'd find them, but it's if they're freely available or if they're available with just a free sign up somewhere, then in principle we can always implement a store for that.
I see Gunnar has his hand up, so maybe he has an answer or he might have another question for you. Go ahead, Gunnar.
No, just a remark. Thanks, Pont. I happen to work with Pont and Clara, so the way it sounded, I mean, it's not us that necessarily has to do this. I think we said clearly, also in the beginning, it's completely open. So it's a license under MIT, so you can do whatever you like, and you are even free to of course write your own store, and we can support with that. But in principle, if the data is in the stack catalog and you use XCube stack, which is becoming the quasi standard for many archives, then you might be, well, at least you have made the first step, and then from there one has to look.
Thank you. Any questions from the audience for either Pontus's overview or Clara's demo? Gunnar, is your hand legacy, or did you have
I'm sorry,
another?
I still raised. I
Okay.
take it down.
Annabella.
Thanks, Mary. Well, congratulations. Very interesting, the webinar and the tool. I will explore it. And the question is if all the products are products from the space agencies, or you have your own products corrected by your own algorithm, for example, for atmospheric corrections inside the data cube. And if the data cube is for all the Earth, I mean, we live in the South Hemisphere, and if you have available also data for the whole world. That's a
I
question.
think Gunnar can probably explain this the best.
Yeah, I may even turn on my camera if it allows me to. Thanks, Annabella. Well, I think yes, we also use our own products. So we, as Mary correctly stated, we have been contracted for parts of the work, but we also use this internally for our own products. So the Cyan Alert one, for example, is our company's product, and we use this internally for work. So that's our working horse, and we market the products, and we apply our own atmospheric corrections and algorithms. So that's, let's say, the technical part of it. That's what we focused on here. And the data as such is not ours. We are not promoting our data here. We're just having a tool to access whatever data. So if the archive is global, in case of the Sentinel-2, you may use it for the Southern Hemisphere as well. And the Copernicus Marine Service has global data as well, and many others as well. So in principle, yes, it's global and free, and the tool is very agnostic. That's why for us, I mean, Pontus and Clara pretty much work on the technical side of it. It doesn't really matter where the sensor comes from and who has paid for it in the first place, as long as the format is somehow understandable by the tool.
And I'm sure they would, I'm speaking on their behalf,
Thanks.
but I'm sure they would welcome feedback from you, Annabella, for how you find the data, if it works well in your neighborhood. Our next question is from Jorgen Vanderbeest from UNESCO.
Yes, hello everyone. As you say, I'm Jorgen from UNESCO, from the Intergovernmental Hydrological Program. First off, congratulations on the tool. Thank you also for very interesting presentations. So at UNESCO, obviously, we also support open science. So we're very happy that this is an open source tool. And just for information, we are working on a water information network system where we have a part of this is a CCAN catalog hosted on an Azure server, hosted at UNESCO, attached to a Terria.js geospatial viewer. So something that we are working on currently is water quality portals and some products from NASA, such as SWOT. Now, a question that I have is, does this XCube allow us to, like, what is its performance regarding on-the-fly requests of time series extractions from geotiffs? Is something that I'm also here with two colleagues. I'm here with Naoya from IHP, and also with our developer Pablo Rojas. So that's the first question. So we are trying to do on the fly abstractions of time series from the satellite products. And a second question is there a active community that is working around this open source tool? And in case we're looking for people that can help us develop on our end, if where this community is based and how we can reach out to it. I wouldn't know who to address this question to, but yeah.
I can perhaps answer at least on the performance question. It's always a very difficult kind of question to answer because there are so many factors involved. You ask about extracting time series analyses from geotiffs. In this case, I would expect that data access might be a bottleneck because I think geotiffs can technically encode multiple time slices within one file, but all the ones I've ever seen in the wild are always just one timestamp, which means if you're trying to get a time series, even if it's a time series for a single geographical point, you might end up having to read an awful lot of data you're not interested in in order to pull out the small amount that you are interested in. So from that point of view, it's very strongly dependent on how the data is structured, and if it's an ongoing, if it's a repeated requirement, then it's often worth pre-processing the data into whatever chunking, whatever format best supports efficiency for the use cases. And this is actually, if there's a well-defined use case, this is really good news, because the worst ones are always, oh, we have this data, we don't know what we'll do with it, probably just about anything, and then there's no optimal data structure. But if you know in advance, yeah, we want to pull the time series out of this, then we'd probably pre-process that into ZAR with very time deep chunks, and that would be efficient for that. In terms of the XCube CPU usage aspect of performance, XCube works with Dask, which is clustering systems. So essentially, you can deploy it in the cloud, and for any parallelizable problem, you can just throw more CPUs at it until the performance is acceptable. I mean, it's Python, so although the main implementation language isn't known for blistering speed, of course, it's interfacing with all kinds of native backend libraries that have very good performance and are usually implemented in Fortran or some other nice high-speed language.
All right, thank you very much. Maybe for the second part of the question on the development community that there is.
Yeah, so as I mentioned in the presentation, we're basically part of this Pangeo community. XCube is one component of that. So there are communities, there are smaller communities around specific XCube deployments, such as DPSDL. So it's really a sort of, I don't know, a sort of meta community of people who use various parts of this Python scientific ecosystem. Gunnar, maybe you can explain this.
I think if you have a specific question, just contact us.
Yeah.
But we are maintaining and owner of the software. It's fully open, but it's the easiest and most effective if you simply drop us an email or write an issue or pull request or whatever you're up to.
All right.
Yeah, maybe I misunderstood the question, but yeah, absolutely. If it's a question of simply support or having something explained, or having a discussion about something relevant to do with XCube, then we're always there for that.
Okay, thank you very much.
I do see, I just want to remind everybody, we are recording today. There's a link in the chat where you can find the recording. It does take a couple hours to process it and upload it, but it should be there for reference and probably about 4 to 6 hours. It'll be posted there, so you can refer back. There was a lot of information shared today. Steve Greb, go ahead and ask your question.
Yes, thanks, Mary Beth. And thanks to the speakers. I enjoyed the presentation and this kind of whirlwind tour of XCube. Kind of related to the last question, does Brockmann Consult offer any tutorials, or is there any training for XCube currently? More of a deeper dive into the aspects.
Maybe quickly. So of course there's documentation, but to be fair, documentation could always be better and more detailed, because we enjoy more developing stuff than unfortunately documenting every bit and piece. But the documentation is a good starting point, and then I think there are some resources out, mostly connected to what Pont already mentioned. There's a deep ESDL platform where we use this, which is sponsored by ESA, and we have a whole bunch of example notebooks that pretty much get you started from very simple things to more complex workflows. And we use it throughout many different projects, and most of them produce material. I think the challenge is here to find them. So also there, if you have a specific use case, and if you simply contact us, we may be able to direct you to the right. It's typically these notebooks rather than let's say readings and videos that are most helpful, because you can simply execute them on your computer and go through it step by step. And the XCube documentation, the DeepESDL documentation, I think we can share the links here, if you can put them in, is
I'll
the
drop that in
easiest
chat
starting
now.
point.
Yep.
And if you get stuck, then that's the right time to ask.
So I'm also happy to share, if Brockmann Consult wants to use today's video, feel free to post this on your website, and I'm happy to. Of course, you'll get the link, but if you would like to have the original file and maybe chop it up into smaller tutorial pieces, I can enable that for you as well. So thank you so much for adding those additional documentation links in the chat, Pontus. I think we have time for one last quick question. We have 2 minutes left. Anybody in the audience have any short questions to ask? Okay, well then let's just give one last hearty round of applause, virtually or in person, for our presenters today. It's nice to see so many of our colleagues from Brockmann Consult also in the audience today. So thank you so much, Pontus and Clara, for your excellent presentation. I know you'll get a ton of views on the YouTube channel afterwards, because it was probably a lot of information. So I hope folks will use that link and look up the video and rewatch it a little bit later. So thank you very much for joining us today. We do have another webinar coming in January, towards the end of January, and we'll share that information on our website as well, if you would like to catch up on that. We also want to make you aware of the Water Talks, which are a special series of presentations by our Early Career Society members. March 19th is the date for that. We do not have the time yet scheduled for that. And just yesterday, we announced our 3 Early Career Society winners of that honor to present their research in the Water Talk series. In the past, we've separated the webinars up, but this year we're going to put them all on one day. So it will be a half a day seminar series, maybe 2.5 to 3 hours or so in length, with breaks, of course, in between the speakers. And we're presenting that on March 19th, which is just before World Water Day, which is recognized annually in March, on March 23rd. So thank you again, and we hope you will join us in the future for our the continuation of our 2025-26 webinar series. Have a great day, everybody, and thank you so much, Brockmann Consult.
Thanks for inviting us. Bye-bye.
Thanks.
Bye bye. Thanks.
Thank you. Bye-bye.
Hi, everybody.